Hello, everyone. Welcome to today's live broadcast, Steps on the Route to Optimizing Experimental Design, including teaching and conducting systematic reviews. I am Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots. So we have a few important announcements before we begin. This presentation has been approved for continuing educational credits. If you want to obtain the credits, please click on the Get Your Free CE Credits button located in the lower left of your screen. This will take you to a page listing all of our speakers and presentations. So please select the CE button under the presentation and follow the instructions to claim your certificate. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many questions as we can. You can enlarge the slide window by clicking on the screen icon in the lower right-hand corner of the slide window. If you have any technical problems viewing or hearing this presentation, please click on the support button at the top right of your presentation window or submit your problem through the green Q&A button lower left. I would now like to introduce today's speakers, Derek Fry, Faculty of Life Sciences, University of Manchester, and Rob DeVries, PhD, Scientific Researcher and Coordinator, Circle at the Central Animal Laboratory at Radboud University Medical Center. Dr. Fry is a medical doctor and also Doctor of Philosophy who's been interested in experimental design since including statistics in his medical student teaching in the 1980s. He continued that interest when he moved to UK government work, which involved assessing proposals for animal experiments in many different fields and advising on biomedical issues in animal-based research and testing. On retiring, he was granted an honorary position at the University of Manchester and has been running or helping run workshops on experimental design in the UK and various countries in Europe, Asia, and North America, and exploring how to teach the subject in an interesting and entertaining way. More on his background can be found on the LabRoots website. Dr. DeVries studied biology and philosophy and has a PhD in the ethics of animal experimentation. As a postdoctoral researcher, he studied the application of the 3 R's to tissue engineering research. Dr. DeVries has been a member of 2 animal ethics committees. His research has always focused on the intersection between ethics and methodological aspects of animal experiments. He currently works as a scientific researcher and coordinator at Circle, the Systematic Review Center for Laboratory Animal Experimentation in Nijmegen, the Netherlands. He is mainly responsible for organizing hands-on training in systematic reviews of animal studies and for coaching researchers who are conducting their own systematic reviews. I will now turn it over to Dr. Fry for his presentation.
Okay, well, what we're going to start with is looking at what you need to think of in terms of optimizing experimental design, and then I'll go on to the way in which you might teach these various things. Basically, I operate on the idea that in order to teach something, you need to have worked out very closely what it is those receiving the teaching need to know, to prioritize it, and to give some idea, therefore, of where they ought to be putting their effort in terms of studying. For optimizing experimental design, I think there are a number of principles you need to pick up. First of all, the ethical principles, and then the basis of providing results that are valid, reliable, reproducible, and as widely applicable as you can manage. But you would expect an optimal experimental design to be efficient in use of animals and resources, and to minimize also the impact on the animal, the severity of procedures, and the distress from the housing and that sort of thing. So the first step, I think, in optimizing is to recognize what is needed. And I think that means a clear objective, getting minimal severity from what you're doing, designing to get good, valid, reproducible results, and also not just taking one experiment at a time, but planning sequences of experiments so that you get minimal severity overall. And of course, for each experiment, getting the right numbers and the right type of design. So for each experiment, you might think about specifying the objective, thinking about the hypothesis, deciding what measures you should take and which are the better ones, considering how you get the best effect and minimize the variability, identifying the experimental unit, and if that's a term which you're not used to, we'll define it a bit later. And you then plan the experimental design, thinking about what controls you need, what are the test alterations you're going to study, what are the constraints, and then how you allocate the experimental units. So you decide how to analyze your results on that basis, taking an acceptable level of significance, that is false positives, and power, which is the ability to detect genuine positives, and estimating the group size on that basis. So those are the sort of thought patterns, but really it's important that you also have an idea of the fundamental principles and keep to them. One we've already mentioned, which is having good and suitable, relevant and usually concurrent controls. Another is to repeat the biological unit sufficiently often to get a good indication of distinctions between groups which have had different experimental treatments. But you also need to make quite sure that you have assigned those particular biological units at random, otherwise you introduce some form of bias. And it's not just when you're assigning, but also randomizing wherever there might be a possible bias throughout the experiment. And this relationship to the experimental unit is key to working out both the replicates, as they're called, and how to randomly assign. And you can define the experimental unit as a repetition unit, or that part of the biological material that can be independently assigned to any of the experimental treatments. For example, if you have this type of approach, you're looking at whether a compound is teratogenic, and you assign a number of pregnant rats to control groups or to one of 3 dose levels of the compound dissolved in vehicle, and then on day 18 of gestation you kill the rats and remove the fetuses and examine for abnormalities. What is the experimental unit there? i.e., what can be independently assigned to a particular experimental manipulation or treatment? What do you think it was? The pregnant rat? The dose level? The fetus? Or is that the sort of thing you're not sure about? Well, basically, what is assigned to different treatments is the pregnant rat. So that is the experimental unit in this particular situation. And then, of course, you need to get appropriate controls, and I think the way of looking at it is to think about what the objective of the experiment is, because if it's simply to compare one procedure as another, you don't necessarily need a separate sham-operated or a vehicle-injected control. You're just comparing the 2 procedures. But then think what the outcomes of an experiment might be, think what the interpretations could be, and then think what controls are needed to avoid misinterpretation. In particular, beware of taking a negative result from the test manipulations as though it was a genuine negative unless you have got some positive control or other good reason for taking it. And of course, randomization, the idea of randomization is to make sure that any inherent problems in your material is randomly assigned or has equal probability of going into any of your treatment groups. So you don't get a mix-up of that property with a particular treatment. And the idea is to avoid bias and make quite certain that what you're getting is a spread of other differences in the different groups that you're comparing to see the effect of treatment. But of course it needs to apply at every stage, because it's not just allocation or selection, but also when you're exposed to a test alteration, when you arrange within an environment where there may be gradients of lighting or heating, and in the order of measurement, because in both giving an agent and in measuring the result, there is a liability for you as a person who's doing it to have a certain amount of drift in terms of your experience and your degree of tiredness, and how near or far you are from a coffee break and that sort of thing. And the problems you find going round is that many scientists don't know how to randomize properly. You therefore get biased results, and you've now got a complete literature which is looking at the problem of the quality of published studies in terms of random assignment and the blinding of the person who's scoring the outcome to the treatment that the biological material has had. Also, people don't plan sequences of experiments unless they're stimulated to do so, and you don't tend to take into account the 3 R's aspect, whether there are possibilities for avoiding animal use or for making procedures which are of lesser severity. And having access to experimental design, at least in Europe, is comparatively rare, and if it does, it comes from statisticians, and they tend to be thinking about the efficiency of design and the numbers and so on, and not necessarily on the severity and the possibility you might have to exclude animals on the basis of the degree of adverse effects that they're experiencing. So the third step, I think, is recognizing that the experimental design is not just minimizing numbers, but it looks at whether there's a possibility of a replacement, whether you're getting pain or distress that may affect the data, and what the animal side of it may have as an effect on your outcomes. But also, you need to think about whether you're using humane endpoints, i.e. cut-off points at which the animal is taken off experiment because of either the severity of the intervention or some other reason has made it impossible to carry on. And you need to have designs which are robust to that sort of loss if it is a risk. And the fourth one, I think, is to have a very clear idea of what you're doing. Because unless you have a clear objective, you can't assess whether the experiment should be a proper testing hypothesis experiment or whether you need some more data, whether you actually need to use animals for that particular objective, and what would be suitable controls. But equally, you can't decide when it should be stopped because you've achieved the objective, or you've found that it's impossible to do it and you need to stop without any further severity or wastage of animals. But also, you can't design efficiently without a clear objective. Now, step 5, I think, is to try and see how you can maximize the effect and minimize the variability, because that has a large effect on the number of animals you need. And the more animals you need, the less optimal one would consider it. What you can do is increase the effect size by getting good measurements, giving larger stimulus, using more sensitive subjects and so on, or you can decrease the variability, usually by improving uniformity, standardizing, or using what is called a covariate approach, or improving the experimental design so it takes into account sources of variability that are not from the experimental manipulations. If you can't do any of that, you need to increase the sample size in order to make sure that you do pick up a genuine effect. And variability has this strange thing that if you have a look at that graph, which is taken with the parameters to the right there, so it's a two-sample comparison, and that gives you, for that measure of variability, the standard deviation there at around 0.4, a size for each of the two groups compared of something like 8 experimental units needed in each. And if you have more variability, then you will need to have larger numbers, and less variability, smaller numbers. But if you look at the variability of 0.6 standard deviation, you find you need nearly 20 animals per group. You drop that to 0.3 3, and you only need 5 animals. So there is a squared effect here. And the more you can cut the variability, the larger the effect you have on the size of the groups you need to compare, and therefore on the animal use. And that's also true with more complex designs, such as this 2x2 factorial. And having mentioned a couple of designs, let's have a look at what they might be. Fully random is simple 2 or more group comparisons. Randomized block gives a certain amount of ability to distinguish variability which is not due to the experimental conditions. Factorial is where you're interested in 2 or more elements that can be regarded as both as part of your experimental outcome. And repeat measures is taking several measures on one experimental unit. Sequential is looking at a little experiment, seeing its result, doing another one which is the same or very similar, and comparing that result and building this up until you reach certain cutoff points which you set beforehand. And these all have plus and minuses to them. The first one is one which so many people use that it's well understood and there's no problem, but you don't get any control of variability which is not due to the differences between treatments. The randomized block does give you some of that control as a variability which is not due to treatments, but it means you lose a certain amount of power. Factorial is looking at 2 different things or more at once and gives you a lot of information provision for the amount of experimental units you use, but it can get too complex. Repeat measure cuts out individual variation, but you have to be very careful that if you're using different time periods, that there is no crossover between the 2 treatment time periods. And sequential is very good for minimizing the animal use, but you need to be very careful how you do it. And I've already used a couple of terms. One is factor, which is really just a source of variability or a discrete characteristic, and treatment for different experimental manipulations, gender or sex, strain, litter, diet, day, all that sort of thing can be used as factors. And blocking is essentially a pattern of grouping according to a possible source of variability. So let's consider a randomized block design in which you do a stratified random arrangement. All the treatments occur in each grouping. So you're comparing the treatments within a grouping or block. And the sum of the values within each block, or the average if you want to go that way, will include a contribution from each treatment. The variability between the sums or averages from each block is not due to treatment, but is due to something else. And therefore, you can see it and take it out of the mathematics you're using to compare different groups. And this is the sort of thing you might do for a randomized block in which you're using different surgical treatments which you're comparing. And here you've got time for A, B, C, D blocks of time, which may be different days of a week or different periods of a month or that sort of thing. But the important thing is that during each time period, every one of the first 4 surgical treatments is occurring. And another illustration is to use litter. If you are looking at 2 different diets and the effect on the pups from different litters, you might group them together like this and get not too great a separation. But if you knew beforehand what litters they came for, you might well find you've got the differences in the litters which are not obvious from the overall pattern between different groupings. So here the red A is above the red B, the white A is above the white B, the black A is above the black B, and so on. And that means you can now see that there is an effect of diet, where it was not clear when you had grouped everything together, irrespective of which litter they came from. Factorial experiments are looking at trying to get that information from several things at once, and they help to show a generality of the findings because they are effectively doing two experiments in one. And to make that a bit clearer, here is a single factor design where you're comparing treatments A and B. A and B are different levels of the factor treatment. You've got 8 experimental units in each one, and you might want to compare 2 strains, so you might go that way and repeat the experiment with a second strain. So you use twice as many animals. The factorial approach is to go this way, and in the comparison of treatments, have half of them in strain A and half of them in strain B. That way you can compare the strains, 1 and 2, against the treatments A and B, and you can, from the whole experiment, work out whether you have significant differences. Because you're using all the experimental units to determine the variability, the individual subgroups can actually be a lot smaller than you might think. But also the advantage of this is if there is effect of one factor on the other, which is called interaction, you can see it. So I think to optimize, a researcher needs to have clear and testable hypotheses to understand how to obtain valid, reliable results using adequate and appropriate controls, a correct identification of experimental unit, and avoiding bias throughout. But it also needs the skill to pick an appropriate and efficient design, and an understanding how to minimize severity because of the effect severity has on the quality of the data. How does one get this across? Having decided that that is what you need to get across, how do you do so? One way, of course, is to present it in such a way that people can remember it and understand why you're arguing for a particular approach. Another way is to get them to look at particular problems and see how they would identify experimental units, for example, arrange experimental units within different treatments, and judge the presentation of the outcomes. And all of those you can use as a way of improving people's skills at identifying what to do in particular their own particular experimental situations. And normally what you would do is also have a discussion, a tutorial type discussion or a facilitated discussion which considers the impact on the animals and how you might be able to cut that down and cut also the variability between them. And I think it's important to have assessment which is not worrisome, so that it is some degree where they have to think about it, but there is no scoring, you don't humiliate anyone in a group situation, and you don't show anyone up in a scoring situation. So you allow them to think about it and to wonder what the answer is, but you never put them in a position where a wrong answer looks stupid. I think that's a suitable point to finish and pass on to Rob.
Thank you, Dr. Fry, for the informative presentation. We will now hear from Dr. DeVries, and I will turn the presentation over to him.
Thank you very much. Now, in my lecture, I want to discuss how a certain type of literature review, a so-called systematic review, can be helpful in designing new animal experiments. And for those of you who have not been able to look at the lectures by my colleagues, Merel Ritskes and Carlijn Hoijmans, I want ever so briefly explain the concept of a systematic review before I discuss how it can be helpful for designing experiments. Now here is the common definition of the concept of a systematic review. It's the process of systematically locating, appraising and synthesizing evidence from scientific studies in order to obtain a reliable overview. So key features of a systematic review are comprehensiveness. You want to be as complete as possible, and transparency. You describe in detail how you conduct the different steps of your review. It's important to distinguish between the concept of a systematic review and the concept of a meta-analysis. They are sometimes used as synonyms, but they are really different concepts. A meta-analysis is a combination of outcome data from individual studies, and you combine those results in an overall statistical analysis. It's important that a systematic review can contain a meta-analysis, but that it's not necessary. For example, if the outcome measures in the individual studies included in your systematic review are too different, it doesn't make sense to combine them in one analysis, and then you have a perfectly sensible systematic review, but it does not contain a meta-analysis. And here are the steps of which a systematic review typically consists. You start by phrasing the research question of your review, and based on that research question, you start searching for all evidence that might be relevant to that question. Based on the studies you find, you select the studies that are really relevant to your question, and you do so on the basis of explicit inclusion and exclusion criteria. Once you've identified the studies that are really relevant for your research question, you extract the main characteristics of those studies, you assess the methodological quality of those studies, so how reliable the results of those studies are, and if possible, you combine the outcome data in a meta-analysis. If you want to know more about the concept of a systematic review, you can look at the video scribe. There's a link at the bottom of the slide, and there you can learn more about the concept. But I now want to turn to what systematic reviews can do for experimental design. In my view, systematic reviews can contribute to experimental design in a number of different ways. And on the most general level, systematic reviews are very suitable to identify knowledge gaps. In a systematic review, you create a comprehensive overview of all available evidence on a certain topic, and so almost by definition, after the review, you know which questions have already been answered in the literature and which questions are still open. And the open questions, of course, can become the research questions for new experiments. But I think systematic reviews can also help in more specific ways. And the first one is by optimizing the design in the context of translational research. Many animal experiments are carried out to inform human health and to get information about human disease. But it's becoming increasingly clear that it's anything but straightforward to translate data you find in lab animals to human patients. There have been a lot of explanations for why it's so difficult to extrapolate data from animals to humans, but one of the factors that's often mentioned is differences in design between the clinical trial and the preceding animal studies. And I want to discuss a clear example of the problems that might occur if there are too large differences between the animal studies and the clinical trial. Let me first give a little bit background information about that example. It's about applying probiotics to acute pancreatitis. Pancreatitis is an inflammation of the pancreas. An important complication in clinical practice is secondary infection of the pancreas. And patients who get such a secondary infection often die. The treatment that is currently standard is the use of antibiotics, but it's not very clear whether they are really effective against pancreatitis, and there's of course always the issue of bacterial resistance. And for that reason, people start searching for alternative treatments. And one of those alternatives suggested recently was the use of probiotics. Now, probiotics can be considered beneficial bacteria, products that contain beneficial bacteria. And basic idea behind using probiotics was that the good bacteria in the probiotics might outcompete the bad bacteria that caused the infection, and in that way it could solve the problem of pancreatitis. Now, to test that hypothesis, in 2004 a clinical trial was started in the Netherlands, and it was called the ProPatria trial. In this trial, about 300 patients were enrolled. Half of them got the experimental group, experimental treatment, so the probiotics, and half of them got a placebo. The probiotic product that was used was called Ecologic 641, and that product contained per dose over 1 billion bacteria. And what's important is that it contained multiple strains of bacteria, so not just one, but multiple strains. And finally, patients got the probiotics twice daily for 28 days in the jejunum. In 2008, the results of the trial were published, and they were rather unexpected. First of all, no differences were found for any of the primary outcomes. They mainly looked at the number of infectious complications in the patients, and there were no differences between the probiotic group and the placebo group. But what was most striking is that the mortality was significantly higher in the experimental group. So more patients died in the group that got the probiotics than in the control group. And one of the questions you could ask about that result is, could this negative result have been predicted if a closer look had been taken at the animal studies that were carried out before the trial? And that's exactly what we did in the context of a systematic review. We looked at all animal studies that studied the effect of probiotics on pancreatitis, and we got some striking results, I would say. First of all, we saw that there were quite some methodological shortcomings in the animal studies. But what was more striking, particularly in the context of my lecture, is that no animal study had a design similar to the clinical trial. We saw that quite a few animal studies applied the probiotics before inducing pancreatitis in the animals. So they were given prophylactically rather than therapeutically. There were some that applied it after, but those used a different product than was used in the clinical trial. We saw that in human patients the jejunum was the route of administration, whereas in most animal studies it was applied orally or through the stomach. And we saw that quite a few animal studies used single-strain probiotics rather than multiple strains. There was one study that used the same product as was used in the clinical trial, but that study applied the probiotics before inducing pancreatitis. So again, a situation different from the clinical trial. And so the question remains, had the animal study been carried out with a design similar to what we saw in the clinical trial, maybe the results would also have been the same, and we would have concluded that it was not safe to use the probiotics in pancreatitis patients, and the patients would not have died. Maybe the results were dissimilar, but because the experiment was never carried out, we don't know. So in that way, a systematic review can suggest which animal studies certainly need to be done before the step to the clinic can be taken. Another way in which systematic reviews can help the design of animal studies is in the selection of the animal models. So once you've decided what the research question of your animal experiment is, you need to select the animal model that's most suitable for answering that question. An animal model here not only refers to the species or the strain of animal, but also, I would say, to the way in which disease is induced in those animals. And in the current situation, that selection of animal models is often not evidence-based, I would say. In an interview study that was carried out in the field of cartilage tissue engineering, we found that the choice was not evidence-based in two ways. So other reasons than the anticipated predictiveness of the model played a key role in selecting animal models. So for example, costs of housing animals, ease of handling were often more important than the anticipated predictiveness. So that's the reason why often small animal models was used rather than probably more predictive large animal models. And the choice was also not evidence-based in the sense that there was not really a comparison between different potentially suitable models, and then an explicit choice was made. And here I would say, again, systematic reviews could help. Systematic reviews can create a comprehensive overview of available models, and you can map the advantages and disadvantages of those different models, and in that way can really provide a basis for selecting the most appropriate model. But even if the intention of the systematic review is not to provide such an overview, a systematic review can also help to provide information that's crucial for making such a choice. What I show here is a figure from a systematic review about the effects of pregnancy on properties of blood vessels. This systematic review was conducted by a gynecologist, and so we really wanted to understand the mechanisms behind changes in blood vessels during pregnancy. But one of the most striking findings in his meta-analysis was that there are large differences in response between different strains of rats. You can see that the Sprague-Dawley rats respond rather differently to pregnancy than the Wistar rats, so different mechanisms seem to be involved. And the Wistar rat in its response seemed to be more closely related to healthy pregnancy in humans, and the Sprague-Dawley rat corresponds more closely to preeclampsia in human patients. So if you want to conduct an animal experiment about the effects of pregnancy, you need to be very clear about whether you want to look at healthy pregnancy or impaired pregnancy, because that has a large impact on which strain of rat you could use most appropriately. So in this sense, a systematic review can also help to select an animal model for new experiments. Finally, I think systematic reviews can help by improving the methodological quality of animal experiments. And again, I think it can be done in two ways. First of all, systematic reviews can show how important it is to take measures to prevent bias in animal experiments. And secondly, they can suggest at which level you should take those measures. But first, why it is so important to take measures to prevent bias in experiments. Here are some results of a systematic review in the field of stroke research, where they looked at the effect of a drug on reduction in infarct volume. And what they did here is doing a subgroup analysis in which they compared the estimated effect in studies that randomized the allocation of the animals to the groups and studies that reported that they did not randomize the allocation of the animals to the groups. And you can clearly see that the studies that did not randomize the allocation overestimate the true effect of that drug. And it's even an overestimation of about 30%. So the actual effect might be quite small and might even be clinically irrelevant. So this clearly shows why it is so important to take measures such as randomization and blinding in your experiment. As I indicated in the beginning of my presentation, a standard step in a systematic review is an assessment of the study quality. And here's a presentation of the different types of bias you look at in such a quality assessment. So you look at selection bias, performance bias, detection bias, and attrition bias. Different levels in an experiment in which bias might be introduced. And so also different levels at which randomization and blinding should be applied. So this composition of the quality assessment in a systematic review might also suggest aspects that you can take into account in designing new experiments to prevent bias. So in short, there are different ways in which systematic reviews can support the design of new experiments. Now, if you want to know more about systematic reviews or about the way in which they can help the design of experiments, you can contact me or my colleagues at Circle. Thank you.
thank you for the informative presentations, both of you. Before we get started on the question and answer session, I would like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many questions as we can, and I'll give you a moment to formulate questions. If there are no questions today, I would like to once again thank Dr. Derek Fry and Dr. Rob DeVries for their presentations. Do you have any final comments?
I could ask Rob a few questions. But I think we can probably do that privately.
Can I just interrupt you for a second? A question has just come in. Do you find that, it's a partial, so it's just part of a sentence. I'm so sorry. It wasn't a complete question. So, as a reminder, this presentation has been approved for continuing educational credits. If you want to, the person says they're sending the full question, so if you can wait just a second, let's give them a chance and see if it comes in quickly. If not, we'll conclude. So while they're formulating their question, I'll just advise that as a reminder, this presentation has been approved for continuing educational credits. If you want to obtain the credits, please click on the Get Your Free CE Credits button located in the lower left of your screen. This will take you to a page listing all of our speakers and presentations. Please select the CE button under the presentation and follow the instructions to claim your certificate. Today's webcast will be available for on-demand viewing through August 4th, 2016. You'll receive an email from LabRoots alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. And the full question has not come in, so I will say see you next time. Goodbye.
Bye-bye.
Cheerio.